Hello, I am Steve Lynch, and my talk today is on how we will use gaming technology to visualize a massive amount of hidden subsurface detail. Before I begin, I'd like to thank Paul for inviting me to give the talk. One positive thing to come out of the current virus situation is that we're becoming comfortable with online presentations. I appreciate the opportunity to introduce a topic that I believe will become increasingly important as we move into the future. One note, because the talk will be highly visual, I won't be on the screen while I give it. I'll see you at the end. The goal of exploration seismology is to produce the clearest subsurface images possible. Notice that I said subsurface images and not seismic images. That's because subsurface clarity has two elements. The first is how clearly the seismic images the geology. The second is how clearly the display images the seismic. Subsurface clarity is the product of the two, and failure of one is failure of both. For the past 50 years, we have obsessed over seismic clarity, but to the exclusion of display clarity. As a result, today we visualize modern seismic that often took months or even years to process, using displays that date back to the era of Pong. Pong is the original video game, and it came out in the late 60s. I played it a lot back in the day, but neither I nor anyone else plays it today. But we do still interpret seismic using grayscale displays, which, coincidentally, were developed by Amoco in the late 60s, at the same time as Pong. But unlike Pong, grayscale displays and all our other displays have hardly changed since. When it comes to subsurface clarity, what the exploration industry has missed out on is decades of development into virtual and augmented reality. But that, in my opinion, is about to change, and seismic is about to catch up. Today's talk is all about virtual reality. It's about what happens to subsurface clarity when we use the same visualization techniques developed for games such as Shadow of the Tomb Raider on the right to display seismic data. And yes, that is seismic data. So, my agenda for today: the strange case of Leo's friend, followed by visual resolution, followed by virtual reality. Then we'll jump into a series of examples, and then I'll come back on the screen for the conclusions. So, the strange case of Leo's friend, subtitled The Evils of Too Many Wiggles. In 1986, I was the processing manager for Western Geophysical in Calgary. The president was a great old guy called Leo Dunn. One day, Leo introduced me to his best friend who had a problem. To meet contractual obligations, Leo's friend had drilled a well at an almost random location, and, much to his surprise, he had struck oil. But this was his problem. He couldn't see what he had drilled into on seismic. Leo asked me to reprocess the line. This isn't the seismic, but it's from the same area, and it will do to make the point. The reprocessing went well, and we were able to recover up to 90 Hz signal. When we did, there, right where Leo's friend had drilled, was a beautifully imaged channel. The following day, I showed the wiggle trace section to Leo and his friend who, much to my surprise, covered his eyes in horror and said, "Take it away! There are too many wiggles." Too many wiggles. He had us filter it back to 1545, like this section here, and that's what he was used to. When we did, his channel disappeared. "There," he said, "I told you. You can't see it on seismic." True story. So the point. Well, first, this is the only time in my career that someone complained that their seismic was too good. And second, I'm using the story to introduce the concept of visual resolution. As geoscientists, we think a lot about resolution, but conventionally we think about it in terms of temporal or spatial resolution. The story of Leo's friend teaches us that there is a third form of resolution that is more important than either of the other two. Visual resolution is defined as the amount of detail that can be distinguished in an image by the human eye. And when you think about it, that is what exploration is all about. What Leo's friend had done by applying his filter was reduce temporal resolution. But who cares? The terms temporal and spatial resolution are abstract. Yes, the filtered image on the left has a lower temporal resolution than the unfiltered image on the right. But what we observe is not a decrease in temporal resolution, but a loss of visible details. Technically, the difference between these two images is frequency content, but what we experience is that the filtered image has a lower visual resolution than the unfiltered image. We can distinguish far more subsurface details on the right. When you think about it, everything we do in acquiring and processing seismic is all directed towards increasing visual resolution. Everything we do is directed towards increasing the amount of subsurface detail in our seismic images. That said, historically, we have always attacked the problem from a data-centric point of view. For the past 50 years, it's all been about the data and never about the image. I'll give you an example. This is an example taken directly from the PGS website. It's showing an example of what full waveform inversion can do, and it's impressive. But think about all the research effort that went into developing this technique, and think about the thousands of hours of processing that went into developing these images. Yes, it was worth it, because the amount of subsurface detail that you can see in the FWI section on the right is much higher than in the original. But after all this has been done, they are displaying the images using grayscale displays, which, as we all now know, date back to the era of Pong. I can't think of a better way to show that we are all about the data, but never about the image. But that is all about to change, because nobody plays Pong anymore, and soon enough, I predict no one will use grayscales anymore, because gaming technology is not just for gamers anymore. Let's talk virtual reality. Virtual reality is defined as the computer-generated simulation of a three-dimensional image or environment that can be interacted with in a seemingly real or physical way. What that means for gaming is that Pong has evolved into this. I'll play a few seconds of it, and when I do, don't just watch the players, watch everyone else in the scene. Virtual reality is the tool, but what we experience is an almost indescribable improvement in the level of detail between these two images. I played the original Pong and it was a lot of fun, but it doesn't compare to the immersive visual experience of modern games. Virtual reality is a tool that increases the level of visual resolution. We have ignored it up to now, focusing on improving our data. But as you will see next, what you're looking at here is nothing compared to what virtual reality can do for seismic. This is the same comparison that I showed you on the previous slide, but translated to seismic. The grayscale image on the left looks virtually the same as it was in the 1960s. The virtual reality seismic image on the right uses many of the same visualization techniques as any modern game you might play, and the improvement in visual resolution is just as stark. But don't take my word for it. That's enough talk. Let's get into data. What I'll do next is look at some interesting data comparing virtual reality displays with conventional seismic displays. The point is that the VR displays have a higher visual resolution because they show far more details. As we go through the comparisons, these are the things to look for: increased amplitude information, increased event visibility, fault plane reflections, and noise train discrimination. My first example will be line 70 from the UK Oil and Gas Association's Rockall Trough project. I use this data quite a bit because it is 2015 broadband data and it's very good. The area itself is virtually unexplored and it's very difficult to explore in because it has a hard water bottom, salt features, volcanic intrusives, a potential subvolcanic petroleum system, and complex faulting. Let's take a look at the line. So this is the line, and as you can see, it is quite extensive. What I'll do now is go from one end of the line to the other, letting you look at the data in detail. As I think it's appropriate, I will switch to conventional displays so you can compare, but I won't say a lot because really this is all about the data, and I don't think I'll have to tell you what you're looking at. And we're back. So I have one other example that I want to show you from the Rockall Trough, and it's this line highlighted in yellow. And what I want to show you is something I've never seen before, and it's called a chemosymbiotic reef. So this is the line, and as you can see it kind of drops off the end of the world here. I'll just zoom in here and show you one of the problems that we have in processing and interpreting this area, and that's this layer of volcanics here, which goes all the way through the project. The petroleum system is beneath it, down here. And we know that because of these things called chemosymbiotic reefs. What you're looking at here is something I didn't know existed before I got this line. And what we have here, this is the volcanics, and underneath it here is what they think is a petroleum system. And it's developing gas, and the gas here is escaping through fractures in the volcanics. I'm just going to change the lighting a little bit so we see it better. So it escapes through these cracks, and you can see it percolating up here. And what happens here on the surface is you get mussels and clams that feed on the methane, building up these large reefs. So what strikes me about this is I have a paper that interprets this, and this is the display that they used to interpret it. Yeah. So this is a typical display that was used to interpret pretty much this entire area, and this is what's in the literature. And as you can see, the amplitudes are really hard to discern here, but let me just put it back to the Wavefield display, and you can start to see just how intricate these amplitudes are, especially in through here. Switching projects. This is another set of data from the UK Oil and Gas Association. It's called the East Shetland Survey, and it was recorded, I believe, in 2018 by PGS. Again, it is modern broadband data, and that's one of the reasons why I use it as an example, plus the fact that it has some fascinating features, one of which I'll show you by bringing up the line in yellow. So this is the line itself. It's line 35A if you have the project, and I brought it up as grey. I haven't put any color on it because there is so much going on in this line that I think the lack of color helps you focus better. Although virtually every part of this line is a month-long study, the area that I want to take a look at is this area here on the right, because you have a series of clinoforms. I'll just move over there. You have a series of clinoforms in here that are called the Dornoch clinoforms, and you have a very interesting unconformity through here. So what I want to do is just look at the incredible level of detail that we get in this seismic using these virtual reality displays. So what I will do now is flip back and forth between this display and the grayscale display, and I will put the amplitudes on and off, and we'll just look at it in various orientations so you can get some sense of the incredible quality in this seismic. Is the grayscale display. You see everything, it's very hard to really appreciate just how good this data is when looked at as a grayscale display. You just can't pick up the details, but once we switch to this focus display, things just become a lot clearer. And if I put the amplitudes on, now we can get a real sense of what's going on here, especially along this unconformity through here. Let's just take a look at this, and this unconformity is interesting because it's hard to follow events through here. On this, when we go to the focus display, especially through here, it's just a lot more detail. You put the amplitudes back on here, and it just absolutely fascinates me, the information that I can get out of this that I couldn't get out of a conventional grayscale display. So this brings me to the end of my talk and to the conclusions. One of the points that I want to make is that the two example lines that I've shown you are in no way special. They were just the lines that I've been working on lately. I have hundreds of lines, and each of them has just as much fascinating information in them. I'll begin by reminding you of what I said at the start, that the goal of exploration seismology is to produce the clearest subsurface images possible. One of the reasons I began with the story of Leo's friend is to highlight the fact that the job is never done. We are always looking for a clearer subsurface image, and in that context we have two good news stories. The two stories are full Wavefield inversion and virtual reality imaging. What we learn from full Wavefield inversion is that we record far more subsurface detail than ever makes it into the final section. What we learn from virtual reality imaging is that there is far more detail in the final section than makes it through the display. We need to put effort into both because ultimately both massively improves visual resolution. I will leave you by revisiting the story of Leo's friend because he has one more point to make. After the horror of applying his filter, we sat down and talked. He began his career in the late 40s, long before the transition to digital signal processing. He knew what seismic was, but he didn't know anything about frequencies or resolution. All he knew is what he was used to. But I explained to him what it was all about and why applying the filter was so damaging. And he listened. Not only did he listen, but he went back and studied and eventually became an advocate for high-frequency processing. Leo's friend was real, but he is an analogy for the entire industry today. The industry has grown up in a data-centric environment, and most geoscientists today understand data, but they don't understand virtual reality and the improvements it can make to visual resolution. Hopefully, I've shown you enough today to convince you that you need to learn. And by pure coincidence, I have the course. So thank you for watching, and I will turn on my video again and answer any questions you may have.